Today, we are going to be talking about an object in motion affected by gravity and drag. We will observe this stress ball to be dropped to the ground and watch its motion over time. Using fundamental principles and basic coding, we will see that data can follow a model of constant force. The fundamental principles we will be using are Newton's second law and the drag force equation. Newton's second law, which is velocity final equals velocity initial plus net force over mass times change in time, will be separated into each variable into the Python code to form predicted calculations. In addition, we will use the drag force equation to predict the calculations with an additional drag force. The drag force equation is a negative drag constant that is determined by the air fluid times the velocity. To set up the data, we will need the ball mass. To find this, I looked up the specific stress ball I used and found out that it weighed half a pound. Converting this to use it in the formula, that is about 0.227 kilograms. Then we will need the initial and final velocities. The initial and final velocities will both be 0 because it starts at rest and the ball finishes on the floor. Since I dropped the ball from my height, I can say that the ball traveled 5 feet and 7 inches in the given time of the video. Converting this, that's about 1.7 meters. To model the predicted motion of the ball over change in time, we use the Python code and separate the variables of Newton's second law to determine all situations of the ball. For example, we use one formula where the weight force is only gravity times the mass of the ball. Another predicted motion was set up where drag was incorporated. I graphed all this data on Excel spreadsheets. My observations show that the ball falls at an increasing velocity. The predicted models show the same thing with a much smoother curve. For the data without drag, the ball seems to fall at a much faster rate than it does with the drag incorporated. With the drag incorporated, the ball ends up at the same position as the observed time graph. This shows that multiple forces are always acting on the ball. Examining velocity versus time, Newton's second law seems to be able to predict the final velocity. By using a small change in time and using the second to last data point, one can find the final velocity of the ball before it hits the ground. What does this data mean? It means that a constant force is being applied to the ball as it falls to the ground. This force is gravity. Now for the what if question. What if the ball was thrown initially down instead of being dropped at rest? If the ball was thrown downward, we would expect a faster terminal velocity. To make sure, we graphed a computer model using initial velocity as a non-zero value. We see that it falls faster than the predicted model with gravity and drag, and faster than the observed model. To briefly examine errors, we see that there's a larger than expected amount of drag needed to be added to the formula. However, this is likely because of an unlimited amount of forces acting on the object. Also, the unsteady observations seen on the graphs is likely due to the blurry ball messing up how accurately the position could be graphed.